back from the break.
Yeah, that's probably good.
And Dr. Stephen LeViness is with us. He's well known in the field of syngas conversion. He worked for about a decade at Exxon and later joined Centrolium, where he worked on catalyst development and scale-up for 8 years. He also ran the online FT database, which is a tremendous resource. He joined Velocys Oxford Catalyst Group in 2010, and he is going to present on new advances on the state-of-the-art of Velocys Fischer-Tropsch synthesis technology.
Okay, thank you very much, Gary. Pardon me, I've been coming down with a cold, so I hope my voice lasts through the talk. Thank you very much for the invitation. I'm honored to be here. I can't add any more than anyone said. You know, Bert is Bert. I remember when I first met him thinking, you know, if I had half of his drive and his energy when I'm his age, that would be fantastic. Nowadays, I think if I had half of his drive and energy at my age, that would be fantastic. But in any case, unlike probably most people, obviously I was familiar with Bert's work, but especially when I was with Exxon, I didn't get out much because of the nature of my job. And I actually got to know Bert working with him on the history side of things, not initially on the catalyst. As Gary mentioned, 10 plus years ago, for a number of reasons that mostly involved Exxon, Paul Schubert and I spent a lot of time tracking down all the German documents, the technical oil emission reels and all of that, and ended up putting it all on the website. And of course, that was something Bert was very interested in, so we did quite a bit of work together on that stuff. Also, last night I found that, you know, there's always connections that you don't know about. Unlike a lot of people, I was not aware that Bert had postdoced with Paul Lemon until the dinner last night. Now, of course, there is a connection there because I did my PhD working for Joe Hightower in Rice University, and of course Joe got his PhD in Paul Lemon's lab shortly before Bert was there, so just one more connection. Anyway, congratulations, Bert. Amazing. I'd like to talk to you about the Velocys FT, and I thank him for the introduction because I'm going to make him look bad because I am going to show a lot of numbers and actually data. On the outline, I'd like to talk about who is Velocys. There's been some confusion, who we are, what we do. And I'm going to turn the presentation kind of backwards from the way it often goes and talk about our FT catalyst manufacturing status up front. A little bit on the microchannel reactor details, although again here I'm going to focus on the catalyst. Quite a bit of information about performance at commercially relevant conditions and performance scale-up, and again some data and discussion of catalyst regeneration and poisoning, and finish with the catalyst composition and manufacturing. At that point, I was going to apologize that I will not be able to show any detailed characterization data, which we do have, but I was not allowed to show it. However, after this morning, I would just have to say that my friends at Sasol and Exxon have already shown that data. So thank you very much. And, yeah, got me out of that line. Okay, Oxford Catalyst Group. It's really two companies originally. Oxford Catalyst was spun out of Malcolm Green's lab at the University of Oxford, which is the top global research center, the largest chemistry department in the West. And Velocys was spun out of Battelle in the Pacific Northwest National Labs. Battelle is the world's largest independent science and technology organization. And really the catalyst technology came from Oxford, the microchannel reactors from Battelle. We have a tremendous amount of IP in microchannels, showing 7,500 granted GTO claims, 6,000 pending. I'm still trying to get us to update how many of those are independent claims. As you know, there can be claim inflation, but we have a lot. We've got about 90 employees now. Our catalyst development group is still in the UK near Oxford, And the majority of our employees are in near Columbus, Ohio, which is a pretty silly place to be when you're in the energy industry, but that is where Catella's headquarters, so that's how we got there. And we are listed on the London AIM market as Oxford Catalyst Group, OGC, although most of our publicity and announcements are under the Velocys brand, and we are actually consolidating the name to Velocys a little later this year. Okay, so the catalyst. There's been a little confusion because we've changed over the years, but this is what it is. It is a particulate catalyst. Okay, it's a powder. It's bigger than a slurry catalyst particle distribution. It's smaller than a standard fixed bed catalyst. And it is directly loaded into small diameter column tubes, microchannels. Typical screens on the top and bottom, catalyst stays in the reactor, but it's also very easy to change out, quite a bit handier than wall coatings and issues like that. We have 2 world-class catalyst manufacturers qualified for manufacture. One made about 1.5 metric tons in 2011, and the other made a single 1.1 metric ton batch last year. We've developed QA/QC, physical chemical properties defined, and can predict performance based on property and characterization measurements. That capacity now is sufficient to meet all the needs that we've looked at as far as potential commercial plants. And importantly, the results that I'm going to be talking about here are all based on operations using these commercial catalysts. This isn't a one-off in the lab or anything like that. So, Sue, to get to your point from earlier, yes, they can be manufactured if you may have to go through a few rounds of scale-up to get over issues and concerns. Okay, the reactor, this is our, what we call the reactor core, with alternating plates. There is a coolant plate, cross flow, and that is boiler feed water, and we are generating steam. Downflow, there's gaps that the catalyst is poured into. So syngas flows down, coolant flows across. Characteristic dimensions are in the range of 0.1 to 5 millimeters. The smaller end is on the coolant side is on the smaller end. The process side is a little larger. Here are some reactors. This is a half barrel a day. It's actually about the size of a pizza box. It's inside a pressure containment shell that we ran with a client in Austria in 2010. This is a 2-foot cube core with a pressure housing around it. That's nominally about 25 barrels a day. And to put it in perspective, that 2-foot cube core at normal operating temperatures will generate between 400 and 500 kilowatts, almost half a megawatt of energy release of steam. This reactor here is a larger one. It's just stacked larger inside a cylindrical pressure containment vessel. This would normally be about 150 barrels a day at standard conditions. It's 4 feet in diameter and 13 feet long. I've had a 150 barrel a day reactor in my career before that I climbed inside and been lowered down on ropes, so it's a little different concept. So for scale up, this looks very much like a traditional or conventional multi-tubular fixed bed system. The key dimensions don't change. In the lab, we run single microchannels that are the full length. They're 24 inches long, and they have exactly the same dimensions as the microchannels in the reactor. We go to a pilot reactor. We add more of them across a single plate. We go to a demonstration reactor. We have more plates. And for a commercial reactor, just even more. But the concept is exactly the same as a conventional fixed bed. Gas distribution by pressure drop, and just increasing the number of tubes. All the parts are the same. The micro-macro interface ensures consistent results on these different scales, and it's simply numbering up. All right, this particular graph, I showed an earlier version of this about a year ago. Some of you were there at the Syngas conference in South Africa. This is CO conversion here at the top, reactor temperatures in red and methane selectivity in green. And this is very similar to the data Kim was showing, except again, I have the numbers on mine. And we're increasing temperature to hold conversion more or less steady, and we were doing a lot of product collection and analysis at each of these periods. One important note, if you see right here, there's kind of a plummet in conversion and then a sharp rise in temperature. We had a trap failure in the lab. People often talk about clean cylinder gas. Well, if you have 3,500 pound CO, it's not clean when it comes into your facility, and if your trap fails, you get carbonate. So over on the bottom here, this is time on stream, and this is in days. This is not hours. Okay. So over a period of about 660 days, we increased the temperature, 27 degrees centigrade. But 8 of that occurred in this poisoning event. So actually 21 degrees of activity loss at FT conditions. And as you see, methane will go up with temperature. Not saying we would ever run here, but we had to get the data before we could determine what the economics would be. Late last year, we did a hydrogen kind of a re-reduction. And typically, that will recover about half of your activity. We heard some discussion of that this morning. A little while later, we did a full redox, kind of standard wax removal, oxidation, re-reduction. And I'll show you the data, but we actually came back at a slightly higher activity here 2 years later than when we first started this up in January 2011. One thing about this kind of data is it's not economic. You can't just run a single stage at 70% conversion. It's kind of meaningless because your syngas plant or your XTL plant would never be economic. Syngas is really expensive to produce. Generally, it's about 50% of plant capital for gas to liquid plants, and it can be a lot more than that for coal or bio. So project economics require maximum liquid production, typically overall CO conversion more than 90%, and C5 plus liquids minimum 80, but should be, again, quite a bit higher than that, which means you want to minimize light gas selectivity. I think we all know that just about zero cobalt-based FT catalysts can run at over 90% conversion. There's kinetic issues with that, getting there, and there's also activity maintenance issues with staying there. So there are two ways to do it. Kim mentioned these earlier. You can run a two-stage or even three-stage if you had to, system 1 through, or a single stage with tail gas recycle. And just to look at those briefly, syngas in an FT reactor, you've got a couple coolers, 3-phase separators. You may or may not recompress here. Then you go to another second stage FT reactor and then cool down, knock out product again. Then you have a tail gas purge from the FT unit that will typically go to a combination of fuel and some recycle to syngas generation like an ATR or SMR. Single stage with recycle is just what it sounds like. You have an FT reactor, some separation, and then when the tail gas comes off, a significant fraction of that is recycled back to the feed. It's a way of achieving high overall conversion on fresh syngas while limiting the per pass conversion in the reactor. And typically when you're at relatively, when you're at relatively low inerts, certainly below about 20-25% non-hydrogen CO, usually the single stage of recycle will be the more economic choice. Just a couple details there. The recycle ratio is really set by the difference between your per pass and your overall conversion. So here I'm targeting 91.5. If we can run 74 per pass, which is our current design, we have a recycle to fresh feed ratio of a little bit over 0.4 and about 30% inerts on feed, starting with a kind of a standard 10% inert ATR kind of gas. If we could only run 60% conversion per pass, we'd have a recycle to fresh feed ratio higher than 1, and we'd have almost 40% inerts on feed. That's just the way it works. And if we try to go to even higher conversion, in this case 94.5, similar kind of thing. Now, we've looked at a design with 80% per pass conversion, and there we need a 0.5 recycle ratio and 35% inerts. But if you could only run at 60, you'd have over 1.5 parts of recycled tail gas to feed. What that does is it backs feed out of your reactor, and you need more reactors. So there's a significant economic implication of the per pass conversion you can operate at. The data I'm showing here is from a laboratory single channel reactor. We feed carbon monoxide, hydrogen separately, use nitrogen as inerts. Although the large reactors are cooled generating water, we actually use a hot oil loop, so it's a little worse heat transfer in the lab. And then we have a number of knockouts, online, GC, tail gas meter, etc., the material balance, collect products. This is a run I started last year, right around the time of the South African convention. And we are simulating the single stage of recycle, calculating what the feed would be at 91.5% total conversion and 74% per pass. And then we're targeting to keep the conversion at 74 or above. And the blue line here, that was for this condition equivalent to 91 to 92% overall. And you see, again, we're doing that regularly. Over the last couple of months, just for grins, because we're still finding out what this catalyst will do, we took this up into the low 80s. Again, this is time on stream in days. So these periods are, in many cases, 30 or 40 days. We're losing 1 or 2, maybe 3% conversion in there. Another one, we lost cooling on the weekend here at about day 50, and the feed did not shut off. The reactor got really hot, as you might imagine any FT reactor will. It was hurt pretty badly. We regenerated this at that time as well, and we actually started up a higher activity after that than we had initially, and obviously, I think you'd agree that the maintenance since then has been pretty good. That effect is more than likely redispersion through the oxidation. It's been observed before. I know Southwell has reported on that. I believe Shell has as well. Okay, now looking at these conditions, you know, that's pretty high conversion to start with. But the other important thing is we're running substoichiometric feed gas. This is equivalent to a fresh syngas of 2.0. So the reactor feed is actually in the rate of 1.75 to 1.85 hydrogen per CO. And that means it goes down drastically when we're running such high conversion, and we keep stepping on this. So this is what our tail gas hydrogen CO ratio looks like during that run. This would be if we had completely stoichiometric feed, 2.1 in, 2.1 out. We're actually down here at 0.6 to 0.8 range, which is a little bit counter to the usual teachings about cobalt catalysts. Now, it's never been as bad as my friends at Rentec will tell you that you have to run 2.1, but I'm a little surprised at how well this runs with these very low ratios. Similarly, because of the low ratio, I think I'm sorry, my friend Raphael isn't here. He was one of the coiners of the 6-bar water partial pressure limit. This is our water partial pressure during that run. The red line is 6 bar. As you can see, we're typically 7 to 8, and in some cases 9 or more, with very little effect on the catalyst at all. Combining the two, another parameter that people worry about is a water to hydrogen ratio. And because we're running spectacularly high water partial pressures at sub-stoichiometric conditions, in these last periods we're up at 6 to 7 to 1 water to hydrogen. It does look like it's coming down very fast because it's two effects combined. The water drops as conversion comes down and the hydrogen goes up. So this is kind of amplifying the conversion changes. And this is what it would be, again, if you had stoichiometric feed. It would be about 1.5 at 70% conversion. So we're operating way over that. This is really busy. Don't worry about trying to write numbers down. We're going to put this presentation on our website probably next week, and we are submitting a paper for the topic of catalysis. volume that will include this. Just a couple of highlights I'd like to point out. GHSV, this is gas hourly space velocity, total feed volume, standard basis per volume of catalyst per hour. It's typically in the 11 to 12,000 ton range. Catalyst productivity on a volumetric basis in the range of 1,700 on the low side to 2,500 or higher. And productivities tend to range from, in this case, the high conversion is a little low, but 0.9 to as much as 1.5 grams of C5 plus per gram per hour. Selectivities, as I mentioned, the target, we'd like to be in the high 80s, and we've got a lot of data here in the 88, 89, 90. The high conversion, that gets hurt, so I'm not really sure how attractive that's going to be economically, but we need to do this in order to get the data. And then I mentioned we collect a lot of product samples, both hydrocarbons and the water for characterization. So here's a result of one. It's a low temperature operation after the regeneration on that previous run. These are paraffins in blue, olefins in red, isoparaffins are yellow, alcohols green, and acids blue. Fairly standard kind of behavior. The alpha is pretty high here. It's about 0.93. One interesting thing, despite the high alpha, the olefin paraffin ratio is below 1 at all carbon numbers, even C3 or C4, and I'm not sure I've ever seen that before on any other catalyst systems. Typically, my experience has been if you're getting a high alpha, you have a olefin to paraffin ratio of 2, 3, or 4 in the LPG. I think that has quite a bit to do with the conditions we operate at. And the total olefins and alcohols are pretty low for cobalt catalysts, as you see, or the magnitude more. We're maybe in the range of 5% non-paraffin products. As you go up in temperature, alpha goes down a little bit. At 210, it's about 0.9, same kind of behavior. Olefin to paraffin ratios are below 1 at all occasions, and the predominant products are paraffin. I should note, Kim mentioned some of his outside business. Emerging Fuels actually conducted these analyses for me, so we're not cooking the books or anything like that. This is Kim's analytical data. All right, last year we ran one of those 2-foot cube reactors at a client site. I'm still not allowed to say where, who, or what, or anything else. Let's just say the syngas composition was very different from what we normally run. So I can't show the data based on kind of our standard conditions. We have spent a lot of time developing a kinetic model over a wide range of conditions, and this shows over a period of 20 days, these are long time averages, what we measured for conversion and methane selectivity versus what the model predicted, assuming 100% of our lab activity in that reactor. And as you see, we're pretty much right on it, or within the scatter of the uncertainty of the data. So we're very pleased with this. This was activated under industrial conditions, recycled hydrogen, desiccant dryer, very low hydrogen makeup rate. Okay, regeneration. I mentioned that really long-term run. We started up this all the same operating conditions here, standard 12,400 GHSV, the rest are listed. 205 to get 71% conversion initially. This is in January 2011. Before we did a re-reduction hydrogen treat, we were up to 232 to get the same kind of conversion. After that, we got down to 217. And we ran a little bit, so there was some deactivation back up to 218. We did the oxidative regeneration, and we came back to slightly higher conversion at 1 degree lower temperature at 1.92 years on screen. So we're pretty happy with that. One thing that does stand out different if you look at the CO2 selectivity, and since there's none in the feed, it's very easy and accurate to measure it. At the same conditions, we've got about twice the CO2 selectivity, which I think supports the iron carbonyl breakthrough in that earlier event. We did another long-term study for this reaction kinetic model, and we really beat this catalyst up. We ran all kinds of stupid conditions all over, and it was pretty badly hurt. After about 300 days, we were up to 226, again, at standard conditions. The re-reduction got us down to 214, and then we repeated the kinetics again on the post-regeneration sample, looking to see if there were any changes. There weren't. And then we ended up about 223. We did the oxidative regen, and lo and behold, we come back 5 degrees higher activity at the same conditions after a little more than a year on stream. Similarly, in a real plant, who knows, with upsets and regular regenerations, you may have to do, over a catalyst life cycle, 5 or 10 different procedures, and it very much is possible to do a regeneration wrong. You can kill the activity, or you can get the activity back and destabilize the catalyst. So it's really important to show that you're not gradually doing harm just with your procedure alone, such that after you've done it 3 or 4 times, the catalyst is not performing anymore. So instead of running for a year or 2 in between each regeneration and taking 10 years to do these studies, what I've been doing is we did go well over 100 days the first time, again with some kinetic work, and then holding shorter periods in between, but just repeating the procedure. You see initially 202 degrees at 73% conversion. After the first regeneration, we're getting 71 at 198. And since then, we've been 108, 98, 199 through 7. We just started up this reactor after the 8th one, and it's at about the same point. After 10, then I'm going to let it run for months just to look at the long-term stability compared to initial values. But you see very good reproducibility here. With the lower temperature, we do get a little higher C5 plus selectivity, but I don't see anything more significant than that. Okay, people have often said, well, your feed rates are so high at 12,000 GHSV, if you've got contaminants, well, you're going to deactivate a lot faster than any other reactor. And that's a valid concern. So another thing that we've done is look at contamination. And while we're just starting to look at contamination, funding issues and management priorities delayed me a bit. These are results from ammonia addition. Now, unfortunately, I cannot specify these as a total ammonia addition rate because of comparable data, I do not know the GHSVs. Or, well, I take that back. I do not know them, but I'm not allowed to say them. So this is publicly available information, and I've just plotted it on concentration of ammonia in the feed. From Exxon, there's a patent that came out in the late 90s. We get a deactivation rate of a little over 10% per day at 100 ppb, and a little over 1% at 10. Centrolium, in fact, I had presented this at a symposium honoring Cal Bartholomew about 6 or 7 years ago in Boston, New York. It's quite a bit lower, but it's not, orders of magnitude different. And our data, which is just over the last several months, is kind of in between the two. So, yeah, ammonia is a poison, but even though we're running 12,000 GHSV, it doesn't seem to affect us any differently than these other technologies did at lower feed rates. I think it's really more active site dependent than anything else. Am I running out of time? Okay, I'm just about done. I'd just like to comment here, because besides that published data, about the only other data I know that's out there, PERC did, a DOE study a couple years ago. And surprisingly, he found that when he added ammonia with cobalt catalyst, it didn't do anything. Now, I've worked with a lot of different ones, and I've never seen that happen. Now, this is a detail to what we did. We put in 1 ppm, and you see it plummet. But it always stops at some level, even with the ammonia in. And if you take it out, it slowly starts to reactivate. We actually did a hydrogen treatment here because we didn't want to wait forever. We reversed all of that deactivation. Now we put 0.1 in, it deactivates slower, and it stops at a higher level. And if you take it out, it starts coming back up. I have seen cases where we had a catalyst that did not respond to ammonia in the field, but we knew that it was lower than expected activity because we had run it elsewhere. And once we got the expected activity, then lo and behold, it started getting poisoned. I don't know what magic you had in that system, Bert, but I've never seen anything except a fully poisoned catalyst not respond to ammonia or cyanide. We do plan to continue with other ones, importantly sulfur and other species which will often be in the gas, doing similar kind of studies to nail this down as well. So last, to just finish up, these results are due to the unique method of catalyst synthesis, not the composition. Okay, if you took our catalyst and did an elemental analysis, it's well within the industrial standards. Nothing would really stand out. Cobalt, standard catalyst support materials, promoters, and PGM promoter content, well within the normal ranges that we've heard about the last couple of days. The microchannel reactor is necessary but not sufficient. You could put another catalyst in this reactor, but it wouldn't pay because the reactor is expensive per unit volume. But the catalyst, if you put it in a conventional FD tubular bed, it's going to melt down immediately. And as soon as you put syngas in, it's all over. And the support is optimized for catalyst performance, not attrition resistance. So if we put this in a slurry bubble column, I'm sure it would be, the filters wouldn't like it at all. We could probably make this catalyst on appropriate support, but that's not the support we're working with now. And it's really the manufacturing. We've published this before. We call it the organic matrix combustion method. Stu was somewhat close earlier today. But there is organic matrix, and we get a smaller and tighter cobalt particle size distribution. And within certain parameters, we can actually minimize the deactivation rate through controlling that parameter as well. There are other things that also influence deactivation. So I think that's about it that I wanted to say. I think we're a leader in advanced FT technology. We've got outstanding maintenance at very aggressive and commercially relevant conditions, and it's a simple, conventional fixed bed type scale-up. We've regenerated over multiple cycles. Poisoning is consistent with published data. And we really don't have any exotic, limited, or extremely expensive ingredients in the catalyst. It's just how we make it. So with that, I'm done. Thank you. And again, Kurt, congratulations.
No, the ammonia we did, you're right, it was at the end of a run.
Okay.
It was aged. We've since run with fresh catalyst and get the same curve you do.
You do?
Yes.
Oh, all right. I'm glad to hear that.
It goes
Actually,
down.
not really. If you had a magic way of stopping it,
No.
deactivated, I'd want to know about
No, just aged catalyst.
that. Okay.
Anybody else? Question or comment? Thanks, Steve. Oh, we got one in the back.
Yeah, I got one question. I mean, you showed very beautiful the concept of the reactor and the catalyst. So, what's the business model?
Our business model is we are looking to supply catalyst and reactors and licenses for, yeah. So we've announced a couple of plants that are in serious consideration. The Salina Blue Sky, it's a municipal solid waste to aviation fuel project in London.
Green Sky.
Green Sky, that's right. And then there's a Calumet Specialty Products small plant in Carn City, Pennsylvania, that's currently in engineering review. So we're not manufacturing catalysts or hardware. We're designing them, validating them, and working with partners in the manufacture. And we would be supplying the catalyst, the reactor hardware, and the licensed operator.
Thank you once again.
Okay, thank you.